Hi there, thanks for joining us. Andrew Dunkley here on a Q&A edition of Space Nuts. And coming up on this episode, we're going to be talking virtual particles, what spins in a black hole besides my brain, and still on black holes, getting a piece of one. Is that possible? And what bit could you get? We'll answer all of those questions on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he doesn't know why, but he's back. Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Yes, I've wondered that. Why am I here?
Well, that's the ultimate question of life, the universe, and everything.
It is indeed.
Why are we here?
That's right. Yeah, that's right. It's yeah. I had a lovely experience at the weekend because I work with a very well-known Australian music composer and called Ross Edwards, and he wrote a work. Yeah, he probably knows music. Very, very well known. He wrote a work probably 3-4 years ago, which was supposed to be premiered in Tucson, Arizona, a major orchestral and choral work, part of which I wrote the words for. And it was a poem that I wrote, which basically is all about why are we here. That's why I mentioned it. But at this weekend, it never made it to Tucson, Arizona, but it had its premiere performance by a choral group called the Song Company in City Recital Hall here in Sydney. So I listened to my words being sung by the most amazing choral group. Just blew my mind away. And it did make me wonder why I was here, but that's what it's about.
And I think you sent me a copy of the lyrics. There once was a man named Fred who couldn't get out of bed.
No, that's the one, yeah. It's a little bit, so slightly more spacey than that.
Yeah, I'm sure it was. Yeah. Shall we try to answer some questions?
No. We can't do
Okay.
that.
Thanks for joining us, Will.
Yeah, let's do it.
Next week.
And it's nice to have an all black hole edition as well. It's
yes, very dark indeed. Hi, Fred and Andrew. Really like the show. It helps me do the washing up. There's a black hole in that. I used to live in Australia, and when I started listening to Space Nuts, I thought that Andrew might be the well-known Sydney Swans fullback. That happens to me semi-regularly, even 20 years after he retired. I live on the Wirral near Liverpool. I have a question about virtual particles. I've found articles on the internet that give a contradictory view of what they are. Some say they are real particles that come from fleetingly in and out of existence. However, the other explanation suggests that they are not real, but a mathematical device to explain how matter and energy behave in empty space. I thought that Hawking radiation was caused by one of a pair of virtual particles falling through the event horizon of a black hole, while the other escaped and became real. I'm sure this is a simplistic description of what happens, and if virtual particles don't actually exist, then not a very accurate one. It would be great if you could set me straight. Best wishes, Martin. Hi, Martin. Thanks for the question. Virtual particles. There's a lot in that question, Fred.
There is, and let's start with the good bit, because I know the area where Martin lives reasonably well, or I did, back in the 1960s, because the Wirral, which is a lovely part of the country, the UK, a little village there called Barnston was where my future in-laws lived, except they were only virtual future in-laws because that all fell through. But I used to visit the Wirral very frequently, so I know the area well and can picture it as it was in 1967.
There you are.
Yeah, so thank you. Thanks for getting in touch from the Wirral, Martin. It's nice to have that reminder of a nice place. So virtual particles, yeah. And now Martin's absolutely right to be confused about this, because everybody is. And a good place to look is the Wikipedia page on virtual particles, because when you read through that, you realise that it's not a case of real and imaginary. It is something a bit more subtle. So, in fact, I picked out from the introduction. Yes. So there's a sentence in here. This is from the Wikipedia article. The accuracy and use of virtual particles in calculations is firmly established, but as they cannot be detected in experiments, deciding how to precisely describe them is a topic of debate. So there you are. Yeah. It's a hot topic. And I think the bottom line is, well, let me read a bit more, because I think this perhaps illuminates it. It is a subtle area, whether these are real particles or not, and they come about because they are a particle description of a field, a bit like the Higgs boson is a particle that relates to the Higgs field. Let me just read. The concept of virtual particles arises in the perturbation theory of quantum field theory, where interactions between ordinary particles are described in terms of exchanges of virtual particles. And so basically you've got, and then it goes on to describe the Feynman diagrams, Richard Feynman, that great physicist who did all these sorts of wonderful things. It goes on to say that virtual particles do not carry the same mass as the corresponding ordinary particle, although they always conserve energy and momentum. It's a good place to start if you want to understand virtual particles. And in fact, just the definition that they give at the beginning of this Wikipedia article, a virtual particle is a theoretical transient particle that exhibits some of the characteristics of an ordinary particle while having its existence limited by the uncertainty principle, which allows the virtual particles to spontaneously emerge from vacuum at short time and space ranges. There you go. That's it in a nutshell. I don't know whether that helps, Martin, but the answer is you're quite right. It's a mishmash.
Yeah. You mentioned Hawking radiation, which we know of.
Yes, we do.
Studies of black holes. Talking about a pair of virtual particles falling through the event horizon of a black hole, one gets captured, the other escapes and becomes real. Is that too simplistic?
I think that's as good a way as any of looking at it. It's because Hawking radiation has never been detected because it's too weak, basically. But experimental simulations have been done. And I can't remember the physics of that, but what you're doing is you're having proxies for the virtual particles. And it turns out that they confirm that Hawking radiation is real. And of course, it answers various loose ends, but it does mean that eventually black holes evaporate, because the particular particles that come off Hawking radiation are photons. And they are, that's radiation. So that's why they carry energy away, because of this virtual and real particle. By the way, virtual photons, according to the Wikipedia article, are the exchange particles for the electromagnetic interaction, which makes sense. Electromagnetic radiation is carried by photons. So, Martin, have a look at that Wikipedia page. It does go on to get into some pretty deep physics with the Feynman diagrams, but nevertheless, I think it was quite helpful. It certainly helped me to realise that, yes, nobody really knows the answer to this.
Yeah, that's the simple answer. No one knows.
No one knows.
Thanks, Martin, for the question. From the UK to the USA. Gentlemen, this is Michael from Evanston, Illinois. Having recently read an article on measuring the spin of a black hole raises a question that I trust you can resolve. You've got a lot of faith. I believe the definition of a black hole is a singularity consisting of a point of infinite density and infinitely small, and an event horizon beyond which nothing can escape. That being the case, the question is, what exactly is spinning or rotating? The indefinitely or the infinitely small and dense point? That is difficult for me to comprehend, but I admit that my thinking is based on Euclidean geometry. Thanks for the great podcast, Michael. Thank you, Michael. Yeah. What's spinning in a black hole, Fred?
No, again, Mike, this is a very similar question to the other one. It's counterintuitive. If you've got a single point of infinite density, how can it have spin? Because a single point in space can't spin, but it does. And the best way to think of it, going back to our old friend Wikipedia, the definition of a rotating black hole is a black hole that possesses angular momentum. So that is the giveaway. And if you think about it, you can kind of understand where that comes from. I think it's easier to get your head around this than it is the real and virtual particles. If you think about a stellar mass black hole, a black hole which has perhaps 20 times the mass of the sun or 15 times the mass of the sun, let me start again. If you think of a star that is going to collapse into a black hole, in other words, one that is perhaps 10 to 20 times the mass of the sun at the end of its life. So this star explodes as a supernova, its core collapses, but the core has itself angular momentum because the star is rotating. So that rotation of the star, and hence of the core that is now collapsing into a black hole, that rotation is still present as angular momentum. It's a property that is conserved. So the collapsing star takes the angular momentum with it when it's forming a black hole. So the black hole itself, despite having no dimensions, has angular momentum. And that, I think, is the easiest way to think. Like an
eddy.
Yeah, maybe like an eddy. That's right. Yes. The classic conservation of angular momentum demonstration where you sit on an office chair and you spin yourself around with your legs sticking out, and then you pull your legs in, and that speeds up your rotation. That's the conservation of angular momentum. If you then collapse to a black hole, you take the angular momentum with you. You'd still be rotating, even though you were a black hole.
How fascinating. So, Michael, looks like you were pretty well on the money, even though your brain is hurting.
Mine is too.
Yeah. He mentioned Euclidean geometry. What's that?
The normal geometry that we experience in everyday life, thanks to Euclid. So Euclidean geometry has parallel lines never meeting. It has the angles of a triangle adding up to 180 degrees. Non-Euclidean geometry doesn't. And we think the universe is non-Euclidean, although it does have, there's a suggestion that perhaps it's almost Euclidean, if I can put it that way. It's what we call it a flat universe. We've talked about this before. Flat is if you've got a flat universe, that's one that has Euclidean geometry throughout. And ours is probably not flat, but it's not far from flat. We know from relativity and from the fact that we see gravity warping space that the geometry is something we call Riemannian. It's a Riemannian manifold is the structure of the universe, which is the mathematical term for the geometry that's embedded in the universe. Your face has gone blank there, Andrew.
I'm just so glad I asked the question.
Yeah, anyway, Euclidean geometry is the geometry that we're all familiar with, and no need to worry about it.
Geometry wasn't one of my strengths at school, but I probably did better than trigonometry and all those other, nometries. I wasn't very good at any of them.
Anometry,
yes.
Yeah. That's a good word.
Yes. I think I just made that one up. Thank you, Michael. Great questions. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, your lots are here also.
Space Nuts.
Our final question, Fred, comes from Josh.
Hello, my name is Josh Williams. I live in Pennsylvania in the United States. My question is, so if you have one supermassive black hole flying at the right trajectory and it was to hit another supermassive black hole, would be able to crack off a piece of black hole? That's my question. Love your show. I listen all the time. Keep up the good work, guys. Thanks. Bye.
Thanks, Josh. That's an interesting question. I mean, we know of black hole collisions through gravitational waves. We know that when black holes get together, they get bigger and bigger.
Yep.
But could a piece crack off, and could virtual particles be emitted? Who knows? Could you get a bit?
Could you get a bit? Yeah. I think the bottom line with black holes is they always merge. So the two black holes coming together at very high velocity, they will basically spin around one another, and that spin will gradually increase in speed, and they'll get closer and closer until they merge. And that's what
then they make a squeaking sound.
They make that whoop sound, that's right, in the gravitational waves. That's what we pick up with gravitational waves, with LIGO and other gravitational detectors. So, yes. So I think bits of broken off black hole are something we're never going to find. I think they only get bigger. They don't split into smaller bits. That's just in the nature of their being. Their gravity is so strong that nothing can escape it. So you're never going to have a bit that's smashing off because the gravity is so strong within the event horizon. Nothing, even light, can escape it.
I don't think I'd want to get hold of a piece of black hole if you could. It's just
not something you want to mess with, really.
It's a great way to lose weight, but it's probably... The trouble is, you'd even with a small, modest-sized black hole, you'd still get spaghettified if you were trying to mess around with it. You don't want that. Yeah. No, it's not something I guess you can ever handle. And we've never actually we've now got images of black holes, a couple of them, and so we know what we're looking at, and we weren't surprised by those images when they were released a few years ago because. Mathematically, we already knew what they probably looked like, and it turned out they looked like orange donuts. But they, but physically speaking, do not touch, I suppose, is the best warning.
Do not touch within, probably several thousand light years. That's right.
Yes, exactly. So, Josh, no, you couldn't grab a bit if there was a collision and a piece broke off. I suppose to qualify that, pieces don't break off, except when somebody's working at your house and Geordie gets interrupted from his slumber.
That's right. It's his lot in life to try and break bits off things, especially bones. Geordie, for goodness sake.
I love him. So great question, Josh, but probably not feasible in the scheme of things, and rightly so. If you have questions for us, don't forget to send them in as Martin, Michael and Josh did, and we thank them for that. You can go to our website, and that is spacenuts.io. Click on the AMA link at the top where you can send audio and text questions, or the Send Us Your Questions tab on the right-hand side. Don't forget to tell us who you are and where you're from. We love to know everything about you, your bank balance, the lot. No, you don't have to tell us that. But if you do have a bank balance and you'd like to become a supporter of Space Nuts, you can click on the Support Space Nuts button.
Nice segue there, Andy.
Yeah. Couldn't help it. Thank you, Fred, as always. It's been a great pleasure.
It does. It's always good. Great to have these questions from our listeners. Keep them coming.
Indeed. All right. See you soon, Fred. And we'll catch you on the next episode coming soon. Fred Watson, astronomer at large, and from and thanks to Hugh in the studio. What's he doing right now? The usual. Much. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.